today we're going to talk about hacking the Franson interferometer, and we are faking an extreme violation of the CHSH inequality using classical light. And this work has been done in cooperation with Ashraf Abdelrazig, Mohammed Borenane, and Jan-Åke Larsson. Jan-Åke and I are from Linköping University in Sweden, and Ashraf and Borenane are from Stockholm University. So what we've done is to hack the Franson interferometer. We've broken the security, and in this talk I'm going to tell you how we did it. So as you know, the Bell inequality is a good way of achieving device-independent security. And I'm not going to bore you with the details. You've heard a lot about the Bell inequality this talk. But basically, the implementation of the measurement stations, they do not matter for Alice and Bob, as long as they violate Bell's inequality. And in this case, they can be sure that their devices are secure. So this attack that we have done basically replaces their source with a faked state generator. And thereby, we can break the security and even can control the bit outputs without Alice and Bob even noticing. So the first step in our attack is to use a result from Makarov's group from 2010, where they blind the avalanche photodiodes. So basically, just really short presentation of this attack is that we create an intensity threshold for the single photon detectors. Usually, a single photon detector would react to even a single incoming photon. But what is done here is that we put a threshold, and everything under the threshold in light intensity is not registered. It's blinded. So for instance, this second pulse here, that gives a click in the detector, while the other three aren't noticed at all. So basically what we do is that we blind the detector with a strong continuous wave laser. And as you probably know, Makarov and his group were able to use this attack to break the security of E91. This was done in 2011. So one thing that should be noticed for this attack is that their fake detector efficiency is quite low, and only at 50%. So the device in question today is the Franson interferometer, and it's a way of achieving quantum key distribution with time-energy entanglement. So what we have is a source, we have Alice, and we have Bob. And the source sends two time-correlated photons to Alice and Bob. And these analysis stations might or might not give a delay to the photon. So what is important here is the time of detection at the different stations. Now, if they are both delayed, both at Bob and Alice, or both not delayed, then they will register the same detection time. And that is what we define as coincident. If they don't have the same detection time, it will be non-coincident, and they will have to discard this event. So in effect, the Franson interferometer has a 50% post-selection, 50% detector efficiency, if you like, even with 100% efficient detectors. There's an inherent post-selection. And if we condition the expectancy on coincidence, then we see that the expected value of the outcomes will be a cosine function. So if we want to calculate the quantum mechanical prediction of the Bell value, we just combine different settings for Alice and Bob and compute the Bell value to be 2 squared of 2, just like we're used to seeing. Now this value is of course greater than 2, so it violates the Bell inequality if we ignore the post-selection. Now the point is, we will do this attack and fake the Bell value 2 squared of 2, even when using local realist states, like the classical light. So as previously been shown in several papers that there exists a local hidden variable model that can mimic the outcomes of the Franson interferometer. This was first shown by Ertz et al. In 1999. So I will just present you this model. This is the outcomes for Alice, and these are the outcomes for Bob. And there are two hidden variables, theta and r. So the x-axis is, you can say it's theta, and the r-axis is r. So if we have hidden variables, say, here for theta and here for r, you can see that the outcome becomes a +1 click in the early time slot. Again, the Franson interferometer uses different time slots. So you can have an early detection for Alice and early detection for Bob, or late and late, for instance. So this E here shows the time slot being early. And this is the outcome for Alice. Now the same thing for Bob, -1L. So you can see that, for instance, the outcome in this example will be +1 early and -1 late. Now we will combine this model of outcomes with the previously mentioned blind data attack by Makarov's group. So let's look at one of the analysis stations. This is, for instance, Bob. And we send in 2 pulses of light with a specific phase shift between them. And the time delay between the 2 pulses equals the time delay of the upper arm. For instance, in this case, with this interferometer setting, we will get a click in the -1 detector. So remember again, the first picture I showed you, we have a threshold, and everything under the threshold will not be registered, and all the high pulses above the threshold will register as a click. So the -1 detector will give a click, but the +1 detector will not give a click. And we can change the interferometer setting back and forth. You can see, for instance, for this setting, we'll get +1 click, and back again, we receive a -1 click. So this specific pulse will give a different outcomes depending on the setting of the interferometer. So we can get +1 or -1 clicks, and this is useful for mimicking the local hidden variable model of Bob. So just changing the interferometer setting, again, is here, the phi setting. It corresponds to a horizontal line, and you can see +1, -1, and then around again +1. This gives a change in the sign of the outcome. And this is just what we want. And changing the R hidden variable corresponds to just shifting the input pulse in time. Nothing special there. So with these 2 pulses sent to Bob, these 2 pulses, we have now achieved the LHV model for Bob. Now for Alice, it's going to be slightly more complicated, because her model, of course, looks like this. And along a horizontal line, we do not only have a shift in the sign, +1 and -1, but we do also have a shift in the time slot. For instance, this line here, you can see it late, and then early, and late, and late, and early, late, and so on. So we need the pulses to change the time slot and the sign by only changing the interferometer setting phi. So first, I'd like to take a short detour and just simplify the LHV model. We make a discretization along the x-axis. So we have pi/4 discretization here. The vertical axis can still remain continuous. Note that we have a parameter p. If we put p to, say, this value here, we can show in our paper that we get the Bell value 2 squared of 2 precisely, just like the quantum prediction. Now, instead of 2 pulses for Bob, we use 3 pulses for Alice. And we have a specific phase shift of these pulses. And depending on the interferometer setting phi, we can get different outcomes at the detectors. So again, you can recognize the amplitudes or the intensities on the output here. This one will give a click, a -1 click in the early time slot. You see here is the early and late. There's a click here, nothing here, nothing here, nothing here, and nothing here. So just by changing the phi value here, we can go to another one. And this might give an early click in +1. Another one might give a late click in +1. And another one might give a late click in -1. So different settings, different outcomes. And this is all made possible by a specific phase shift of the input. Now, we can always find a good phase-shifted input here. We can always compute how this should be according to the recipe of the LHV model. I'm not going to bore with all the details of this. This is all in the paper. But I can at least tell you that it is always possible to find a good phase-shifted input for a specific outcome. So basically, phase-shifted input pulses do the trick for us here. So again, shifting the phi value will shift the outcome from +1 late to +1 early, -1 late, and so on. So our 3 pulses lets us achieve the LHV model for Alice. And we have made an experimental implementation of this attack. I will go through this briefly. I hope you can see it all the way to the back. So basically, Eve replaces the source, the local or the normal source, with her faked state generator. And Alice and Bob are none the wiser, but the source consists of first a continuous wave laser and a pulsed laser. And the continuous wave laser is to achieve the blinding attack by Makarov, and the pulsed laser sends single pulses out into this coupler. These beams are combined and split into independent arms for Alice and Bob. And this one is the same as this one, so I'll just show you here. We have a twitter that splits the pulse into 3. And then we will have different delays. We have no delay first in one branch. We have 1 delay and then 2 delays, basically giving us 3 pulses. And then in the different arms, we'll have different phase shifts for the middle and the late pulses output of the source. And then when they're combined and sent to Alice, she will receive the 3 phase-shifted pulses that I talked about earlier. And then, of course, the analysis stations, so the interferometers here, are just like the normal Franson interferometer. Time delay loop, and then the phase shift and combiner, and then plus and minus detectors. So what are then our results? As I said, in theory, our model should give us 2 squared of 2 of the Bell value. So this is our experimental result. We clearly see that the Bell limit at 2 is violated by our result. So we have the Bell value 2.5. Now, the reduction from the theory, from the model, is due to noise. Oops, due to noise. So you can clearly see that this violates Bell's inequality, even though we're using classical light pulses. So basically, we have achieved our attack. Good. But there is more. We can do even better than this. So we just showed 2 squared of 2. And you remember the parameter p? Well, we can let this parameter go to 0. So I just take some arrows here, and we pull the model until p becomes 0, and we land in this. So now we just have rectangles and no complicated model at all, just rectangles. So if we implement this, it's just a matter of doing different outcomes in the experiment. We will have an extreme violation of the Bell inequality, namely the value 4. So the experimental results for this will be a Bell value as high as 3.6. Now, I don't recommend you going out and trying this experiment at home, because Alice and Bob would be quite suspicious of a result like this. So it would think, do I have a popsicle Rolex box here? That would be really strange to them. But the point here, we still have the same efficiency as last time, 97%. And we can tune this. Remember the noise in the last slide? Well, we can compensate. We can combine our noisy result with a better result and land at any result that we want. In this case, I can show you exactly 2 squared of 2 on average. So basically, we have a tunable attack that can reproduce any value from 0 up to 3.6. And it's, of course, a very clear violation. The noise is quite small here. So you might ask yourself if there are any countermeasures to this attack. Well, first of all, we need to know why the attack is possible. And this is because the aforementioned 50% post-selection that actually is inherent in the Franson interferometer. So we cannot have fully efficient detectors and hope to be immune, because this happens even if the detectors are 100% efficient. So there's a possibility of switching the settings very fast. This is described in the paper here. But that will not be enough, because then the Bell inequality, the effective Bell inequality for the Franson interferometer will not have 4 on the right-hand side, but will have 3. And 3, as you know, is more than 2 squared of 2, so it does not help us at all. There's one thing that is possible, and that is the chained Bell inequality as described by Brownstein and Caves. Now, this will give us a violation of the Bell inequality, but it has really high experimental requirements. I think the required visibility is around 96%, and this is quite difficult to achieve. So the Franson interferometer does have some problems with the post-selection, so we might have to look at some other solutions to get good time energy entanglement Bell violations. For instance, we have a poster here that is called Genuine Time Energy Entanglement. By the way, I would love to speak to the poster author. I have been at the poster several times, but if the author could come to me afterwards, I would like to talk to you. They call it Genuine Time Energy Entanglement, and you can find more about this in these papers here. It's been demonstrated experimentally over 1 kilometer. And this is not a post-selection loophole. We have 100% efficiency of the system itself. So this could be a possible way of solving the problem. There's also a possible method by Strakov from '96, where we use polarization entanglement and time energy entanglement at the same time. So we have a little attack that I've just shown you, and the basic ideas here are that we have the possibility of having extreme Bell violations, even up to 4. And it is possible to have this attack even at the high efficiency that we showed, which is 96.7%. We can also compensate for noise, as you just saw. And we can make all the output statistics of Alice and Bob to look just like what they expect. Even the joint outcomes are just what they expect. Early, late, we have plus and minus 1, we have everything matching the theory. So they don't notice the attack at all. And it also works even if the detectors were 100% efficient. It doesn't help them. So I'd like to thank you for your patience, and thank you very much.
I have a question about your experimental implementation. Yeah, could you go back? Yeah, oh. Yes, yeah. Here. So for Alice and Bob, for your Franson interferometer, the phase changes in your experiment? Because generally they will change with the temperature or...
what was the question?
The phase of your interferometer, does it change? Generally in the experiment, we need a feedback system to make it stable. Do you use a feedback system?
We have just made a simple proof of concept implementation, but for any real experiment, you will of course need phase stabilization.
Oh, yeah. That may be my problem. Think about if in the practical scenario, there is a central station distributed in tangle photon pairs. One Alice, for example, in this city, Bob in the other city, and the phase, remember the phase in the different lab or different city, the changes, right? And you use a feedback system. From that sense, if you want to attack it from your center, for example, for the source side, you need to make sure that the phase, for example, if you are using the 2-pulse attacking scheme, the phase difference of the 2 pulse must be same to Alice phase, right?
Well, we match the possible...
Must be identical to Alice phase. But how did you know the phase of the Alice? How do you know the phase difference in Alice's interferometer?
Well, we don't assume that we know Alice's phase setting. That is, of course, impossible. So we adapt to the possible phase settings that Alice might have. So depending on the phase shift, that I'll show you, if she has one setting, she will receive +1, and the other setting, she will receive -1, for example.
Yeah, I mean, actually, my problem is just the reference frame, the reference frame problem. How do you know the reference frame of Alice and your source reference frame are the same?
Well, I mean, this is just a lab demonstration of proof of concept of the system, so that will just be a technical way of implementing it.
Yes, yeah. My question just like, it may be work for the lab. It may work, of course, you give the data, but for the practical scenario, I guess you need to figure out the reference frame of Alice. But I'm not 100% sure, but I think you need to be,
Yeah, you're right. You will need to figure out the frame, yes. But I mean, this just shows that, in theory, we don't have security from the system. We will need something else with the post-selection.
So if you couple this with if people use this for a QKD measurement, then the light that is coming from the source is going to be randomly chosen to go to either the key generation part or the Franson interferometer part. So would that easily fool the, when this goes into the generation part, would that be easily detected? Or is your blinding attack also take care of that?
So you mean, of course you can detect the blinding attack. There will be a technical countermeasure to this, yes?
Assuming that if I don't use any counterattack, I just have, split it and just measure the timing. Does your blinding attack also take care of that?
I would say yes, if I understand the question correctly. Eve can control the bit outputs of the key generation with this.
You can also test Bell's inequalities with non-maximally entangled states. And here you could do that, I guess, by changing the first beam splitters of the interferometers. The question is, do you have a sense of whether or not this general scheme can spoof any value of entanglement? Or I would think that it might be able to, but sometimes things that are non-maximally entangled are actually harder to spoof than things that are maximally entangled.
Well, we can achieve any value from 0 to 3.6 or 4, depending on theory or experiment. So, I mean, we can probably spoof anything that you throw at it, I would guess.
Yeah, but what you achieve depends on the reflectivity. Are you assuming a particular reflectivity of the beam splitter already? So if you change the reflectivity of the beam splitter, I'm not sure that you'll be able to get anywhere from 0 to 4. Maybe you will, but I'm not sure that you will.
Do you mean to change the reflectivity of this beam splitter? Or? Okay. That was news to me. I have to look into it before giving an answer. So.
Okay.
Yeah.